Okay, now we're going to talk about the marginal entropy and joint entropy and conditional entropy as we did with probability. So we talked about marginal distribution and joint distribution and the conditional distribution. Likewise, we can talk about a couple of different entropies. First, marginal entropy of X is simply this one, or if P of X is continuous, then it will be like this. Okay, and the joint entropy H of X, Y is defined by this one. So in this case, it's quite simple. Instead of X, we use X comma Y. Okay, that's it. And what about the conditional entropy? It's a little tricky here. So we have Y given X here, and we have Y given X, but this one is X and Y. Okay, this one is conditional entropy, but it is actually expectation of this conditional surprise with this probability. Okay, so this one is actually expectation of log P Y given X. And this expectation is over X and Y. Okay. Now, let's try to prove, let's prove this one. Okay, the joint probability of X and Y is conditional probability of Y given X plus marginal entropy of X. So we can actually we can write down these terms. Okay, so we have joint entropy here, and we have conditional entropy here, and we have marginal entropy. So let's rewrite this marginal entropy in this case. So let me use just integral. Okay, so that's much easier for me to draw. P of X dx. Okay, this is marginal entropy, and instead of P of X, we can use P integral Pxy dy and log P of X dx. Okay, so this one is exactly the same as P of X. Okay, so now we have a P of X, and log P of X has nothing to do with Y, so this one can be rewritten by P of X Y and log P of X dx dy. Okay, so this one is our marginal entropy of X. And then look at this one. And when we when we actually add this one to this one, then it is actually minus integral. We have the same term here, X and Y, a probability of X and Y, and log P Y given X, this one, and plus log P of X dx dy. This log P of X is coming from here. Okay, then let's rewrite this term. Log P Y X joint probability over P of X times P of X, which is Pxy times log P Y X dx dy, which is the same as this one. So we just proved. Okay, So now I think you become an expert in entropy. Okay, good. So you know pretty much everything about entropy for machine learning. Okay, so we have a little more than just entropy. The next topic is KL divergence or Kullback-Leibler divergence. Okay, so this KL divergence is a divergence between two probability distributions P and Q. Okay, so given two distributions, then we can actually check how different they are. Okay, how far P is located from Q. Okay, so this KL divergence is also known as relative entropy. Okay, KL divergence is actually defined by this term or this term. So if we decompose this KL divergence, then we have cross entropy as the first term, and the second term is actually entropy of X. Look at this equation. This one is just entropy definition, and in this looks like an entropy. It looks like an entropy, but it's slightly different because we have Q here instead of P. Okay, if we have a P and P, then it is entropy of X. But if we have a Q, it's a little different distribution, then it's cross entropy. Okay, and then we're going to talk about this cross entropy later. And this cross entropy is really popular in machine learning as an objective function in the image classification or in the language model. And in general, in supervised learning, we usually use a cross entropy a lot. Okay, so this is KL divergence, and KL divergence is always positive or equal to 0. So it means KL divergence cannot be negative. And here is an interesting point. KL divergence is not symmetry. So KLPQ is different from KLQP. So if you look at this equation, then you can get that, right? So if we change, then actually the KL divergence is different. So since this is not symmetry, so it is not, KL divergence is not a distance, it is a divergence. So somehow it's kind of distance between two probability distributions, but technically it's not a distance. Okay, now let's think about empirical approximation to find the model Q with parameter theta. So now we have a true distribution P, okay? And then we want to model a P with the Q, and the Q has a parameter theta. So we have a true distribution P of X, and Q is a probability distribution with parameter theta. Okay, then if we write down this K divergence one more time, then it is K divergence will be minus log P of X times log Qx given theta dx minus integral P of X log P of X dx. Okay, this one is actually expectation of this one. So let me rewrite this term here. Minus expectation of log Qx theta. And this one is also an expectation of log P. So expectation of log P of X. Okay, so we have expectation, but we cannot calculate this expectation exactly, so we use MC approach, Monte Carlo approach. So we take a lot of samples, instead of using P of X, we just take a lot of samples to approximate this expectation. So instead of using this expectation, we actually take samples. We use just n samples and obtain these values, and then we take an average. Okay, and then instead of this expectation, we take an average. So this is an approximation of a k divergence between P and Q. Okay, and if we want to minimize this k divergence, then we actually update this theta. Okay, that's how we learn some objective function. Okay, then there is another interesting point of k divergence. So you have to understand this. You have to understand the difference between n projection and I projections to use k divergence in the right way. And as I said, k divergence is not symmetric, as you can see in these equations. And if Q is the set of all Gaussian distribution with diagonal covariance, which means Q is a probability, or Q of x given mu and sigma square. So we are interested in this distribution, and when we updated this mu and sigma square, then we might have slightly different Q. Okay, so this is our model, and again we have a true distribution P. Okay, then now we want to minimize. We can minimize k divergence between P and Q, or we can minimize k divergence between Q and P. So since they are asymmetry, so they have different kind of result. Okay, so let's say P is a Gaussian too. Okay, then as I said, as this statement says, we assume that the Q has a diagonal covariance. So Q is always something like this. Okay, it's a circles. And if we minimize this k divergence, then the Q will be like this, these red circles. And the green one is true distribution P. If we minimize k divergence between Q and P, then with the same true distribution P, then the Q will be like this. Okay, it's much smaller than before. So why do we have this kind of different result? Why? So in this case, on the left side, for example, this blue dot should be explained by Q. Let's check this equation one more time. So we actually draw the samples based on the probability of P. Okay, because this expectation is about P of x. So we draw the samples from distribution P. Okay, so what I'm saying is that P is actually generating the samples, and then we minimize the distance between the P and Q with respect to the samples. Okay, so the samples are coming from these distributions, and we are focusing on these samples. And if you narrow down the interest of this Q, even though Q is covering these areas, but when we calculate the distance between the divergence between the P and Q, then we are focusing on these areas. Right? So if we focus on this area with Q distribution, but still then on this area they look similar. Okay, again the Q is supposed to have a diagonal covariance matrix, so it should be a circle. If Q can have any arbitrary covariance matrix, then probably Q will be like this, like a green curve. And then in this case, okay, so we are actually generating samples from Q because Q is the first distribution here. So we don't care these green distributions because the samples are coming from this thing, okay, from this distribution. If we increase the covariance, then the distribution look like this. Okay, then if the covariance is big enough, then from Q we might have these samples, these blue samples. But if we generate these samples around here, then it cannot be explained by P here. Okay, so P thinks, the distribution P thinks this is quite strange. But Q generated this one. But if we delete this one, so now we have Q like this. Okay, now Q is quite small. Then Q is not generating any samples around here. Okay, then think about this one. So samples are around here. Then Q and P might have the kind of similar kind of opinion about these samples. Okay, but if we generate some samples like this, then P might think this is quite strange. So if we minimize this K divergence, then this is kind of optimal Q. So you have to understand this difference. This slide explains the same thing with different the figures with different example, and the px, if px is a multimodal. Okay, multimodal means in the one-dimensional space it looks like this. Okay, we have two modes here. It could be three modes. Okay, so multimodal means we have multiple modes, and the q of x is diagonal Gaussian. Then let's minimize this k divergence. Then samples are generated by this blue distribution. Then with these samples, then Q should actually model these samples, which means Q should look like this. Okay, but if we minimize this K divergence between Q and P, then the samples are generated by Q. Then Q should be this way or this way. Okay, so we cannot have both at the same time because Q is diagonal Gaussian, so either of this one or this one would be possible. Look at this one. The Q is generating the samples from this distribution, and then when we focus on these samples, then Q and P might have the same kind of opinion about the samples. And in this case, if we generate the samples with this Gaussian distribution, then the Q and P might have the same kind of opinion about the samples. Okay, so you have to understand the difference between this one and this one. And in this slide, we're going to talk about mutual information, which is the amount of information that both x and y have. Or we can say it measures how much information x and y share. Okay, so mutual information of x and y can be defined by this one. So look at this one. And this one is actually divergence between these two distributions, p of x and y and p of x times p of y. If p of x, if x and y are independent, then p of x and y is actually p of x times p of y. That means if x and y are independent, then this one is a 0. Okay. So if x and y are independent, then they don't share any information because they are independent. But many times, and x and y, they are not independent of each other, and they can share some amount of information. And the mutual information actually measures such kind of information that x and y share. So This one is measuring how much x and y are independent. So we actually check the divergence between this distribution and these distributions. And it can be rewritten by this line, okay? And the more independent x and y are, the smaller mutual information is. And we can define the relationships between the mutual information and the entropies, marginal entropy and conditional entropy and joint entropies. So mutual information of x and y is actually entropy of x minus entropy of x given y. And let's take a look at this Venn diagram. Okay, so this circle indicates the amount of information that x has, so which is h of x, and this one is h of y, and this red part is actually h of x given y, which means when y is given, then y is already known, then this part is certain. Okay, so we cannot have any information from this side. So this one is h of x given y. Then h of x minus h of x given y is actually this part. Okay, and likewise h of y minus h of y given x. Or if you look at this Venn diagram, then h of x plus h of y means we count this part twice. Okay, then h of xy means the information of x and y, so it corresponds to the kind of union of these. And then as I said, h of x and h of y count this area twice, so this one minus h of xy means this mutual information part, etc. And now we're going to talk about cross entropy, which is quite important in classification or in supervised learning in general. So it measures the similarity between Q and a target P. So again, this one is about the supervised learning, which means we have a label, which is a target P. And the Q is actually estimated distributions from neural network or from other machine learning models. And this cross entropy is identical to K divergence up to an additive constant. So if we rewrite this cross entropy, then it is actually entropy of P plus K divergence between P and Q. And so when we talk about K divergence, we already talk about this cross entropy and entropy. Okay, so cross entropy is defined by this one. As I said, it is a popular loss function in machine learning. So we want to minimize this cross entropy. So as I said, this one is a target label, target distribution, and this one is our estimation. So we want to minimize the divergence between the P and Q, but h of P is fixed. As I said, P is target distribution, so we don't actually change P. So we actually update Q to minimize K divergence. So we don't care this part that much in learning. So we actually focus on this cross entropy part. And usually P is the target in one-hot representation. Think about this classification. So we have 5 classes, and if it is the second class, then the distribution of this one is 0, 1, 0, 0, 0. If the target class is the fourth class, then it is 0, 0, 0, 1, 0. Okay, so this one is actually a distribution. This one is also another distribution, but we call them a one-hot representation. But still, one-hot representation is also a distribution, and the Q is the predicted probability distribution. So we want to minimize the K divergence between these two, or we just minimize cross entropy between P and Q. And the next one is not that popular, but I think this is quite important concept. In entropy or in mutual information, we don't talk about the directions. Okay, so when we have X and Y, and the mutual information measures how much information can be shared by X and Y, but it doesn't talk much about which one is causing the other one. Okay, so the mutual information doesn't talk about that, and instead causality can be represented based on the information flow. How much information is flowing from X and Y. So we can measure that kind of thing. That can be defined by transfer entropy, which was proposed by Hans Markov, and recently transfer entropy was reintroduced by Schreiber in 2000, and it measures how much information flows between variables. And as I said, this one is different from mutual information. And contrary to Granger's causality, transfer entropy is nonlinear. This one is linear between many different variables, but transfer entropy is nonlinear, but only works on binary relations. And first of all, we can understand this free information, which is conditional entropy. Entropy of X given XP and YP. XP and YP indicate the past information of variable X and Y respectively, which means this one measures the information of current X independent of Y. Current X means we know the past information of X, and we know past information of Y. So we know the history of X and Y, and when we measure new X, then how much information we can get. Okay, so this is simply a conditional entropy, but in this definition we have temporal information. And the transfer entropy measures the information in current X coming from Y. Okay, so this one, transfer entropy, can be defined in this way. So h of x given xp means only when the past of x is known, then how much information we have from x. And we subtract this entropy. As I said, this one means the amount of information of x when we know the past of x and y. So by subtracting this part from this one, transfer entropy says the amount of information of current x coming from y. It's not from x itself. Okay, it's from the y. And by transfer entropy, we could actually measure the information flow between many different the variables. This is one application that I had worked. Okay, so we measure lots of variables. Okay, so we have eye tracking, and we have motion capturing, and etc. So we have a lot of variables. Okay, and then we actually calculate the transfer entropy between all of them. Okay, then we can see which one is causing another variable. So for example, when the mom's head movement is following the baby's head movement, then it means whenever baby moves, then mom follows. Okay, then we can measure that kind of thing based on this transfer entropy. Then based on this one, actually we can confirm the psychological discovery, okay, or psychological knowledge based on these quantitative measures. Okay, and that's it. And if you have any question, email me.